Hey guys, today we're doing Chapter 2, Section 5, which is on exponential models. So, exponential function, we've already talked about the definition in the last section, but it's always f of x equals ab to the x, where a is non-zero, b is greater than 0, and b is not equal to 1. Remember that a stands for your initial value, so that's the initial value that you start with, or whatever your starting value is. Okay, b is your growth factor, so that's how much you're growing by or decaying by, depending on whether it's a number greater than 1 or a number between 0 and 1. So if your b value is between 0 and 1, so like it's a fraction or something like that, that would be a decay. If your number is greater than 1, that would be considered a growth because you're getting larger each time. Okay, let's look at this first problem here. A population of a certain cell type was observed to be 100 on the second day and 2,700 on the fifth day. Assuming growth is exponential, find the number of cells present initially and the number of cells expected on the seventh day. So to start this problem, I'm just going to start by talking about my two data points. So I've got population and I've got number of days. I'm going to say days and population. So days is my x value, population is my y value. So the points that I have are 2, 100, and 5, 2700. I also know that I have an exponential growth here. So I've got a b to the x. So what I can do is I can plug these into my equations here. I can say that a times b to the second is 100, and a times b to the fifth is 2,700. Okay, now what I'm going to do is I'm just going to rewrite these as ab to the fifth equals 2700 over ab squared equals 100. So I'm basically dividing these two functions. I put the bigger exponent on top. Now when I divide these, my a's cancel. B to the fifth over b squared is b cubed. And then 2700 over 100 is 27. Now if I take the cube root of both sides, so I'm raising that to the 1/3 power, I get b equals 3. So I found my b value. Now I need to go back through and I need to find my a value. So I'm going to plug this back into one of my original equations. It doesn't matter which one, I'll just pick this one. So I'll say a times 3 squared equals 100. So that's a times 9 equals 100. Well, if I divide by 9, then I've got a equals 100 over 9. So that means that my function is 100 over 9 times 3 to the x. And of course I wrote this with using x, but you could have written it with d and p, that's fine. Okay, then I want to find the number of cells present initially and the number of cells expected on the seventh day. Well, I found the number present initially, it was this number. And then the number of cells expected on the seventh day, all I'd have to do is plug a 7 into this function. So I've got f of 7, that's going to be 100 over 9 times 3 to the 7th. Okay, when I plug that into my calculator, I get 24,300. Alright, my next problem, a certain substance has a half-life of 24 years. If a sample of 80 grams is being observed, when will only 5 grams remain, and how much will remain after 50 years? Well, with this problem we don't really have a lot of information, but we do know about half-lives. I know that if something has a half-life of 24 years, that means that after 24 years, half of the sample is left. So I'm just going to kind of make a little table here. I'm going to have the number of half-life periods, and then I'm going to have my t value, which is the number of years, and then I'm going to have my amount, so the actual amount that I have. So after 0 half-life periods, which is 0 years, I know that I would have 80 grams because that's what I start out with. I start out with 80 grams. I also know that A is 80 because remember A stands for my initial value. Okay, after one half-life, that's 24 years, and I'll have 40 of my sample remaining because I know that after every half-life, my sample cuts in half. So then after 2 half-lives, that'll be 48 years, and then I'll only have 20 left. After 3 half-lives, let's see, 48 plus 24, that gives me 72. And then I'll only have 10 left. So this is kind of what's going on with my sample here. And basically now I can use these data points in order to do the same thing I did on the previous problem and solve this for my A and my B. So I know I have the point, let's see, 24 and 40. I also have the point 0 and 80. Okay, so I'll just use those 2 points. That'll be easy enough. So I can say 40 equals 80 times b to the 24. And then I can divide that by 80 equals 80 times b to the 0. Okay? So when I do that, b's become 1/2. Okay, my 80s cancel. B to the 24th over B to the 0 is B to the 24th. So essentially what I'm going to do is I'm going to raise each of these to the 1 over 24 power. And when I do that, I get a B value of 0.9715. Okay. So now I can rewrite my equation as 80 times 0.9715 to the x. And then it asked me, how much will remain after 50 years? Well, if I plug 50 in here, so f of 50, that'll be 80 times 0.9715 to the 50th. When I plug that in, I get 18.876 grams. And that's how much of my sample remains after 50 years. And that's everything for section 5.